So we are to discuss the topic about undecidability and intractability. Undecidability is the non-existence of an algorithm or the impossibility of disproving a statement within a formal system. The non-existence of an algorithm for settling a given problem is often referred to as the unsolvability of the problem. For example, the totality problem. The totality problem decides whether an arbitrary Turing machine M halts on all inputs. If it does, it computes a total function. This is equivalent to the problem of whether a program can ever enter an infinite loop for any input. So we prove that the halting problem is reducible to the totality problem. That is, if an algorithm can solve the totality problem, it can be used to solve the halting problem. Since no algorithm can solve the halting problem, the totality problem must also be undecidable or unsolvable. So having proved that the halting problem is undecidable, we use problem reduction to show that the other programs are undecidable. Proof. Given the Turing machine M with input W, we construct another Turing machine M prime, which is an arbitrary Turing machine which runs the input MW. So this is the arbitrary Turing machine M prime with input MW accepts if M the Turing machine M accepts input W. It rejects if M doesn't accept the input W. So note, the arbitrary Turing machine M halts on all inputs if and only if M accepts the input W. Therefore, an algorithm that tells us whether the arbitrary Turing machine M prime halts on all inputs also tells us whether M halts on input W, which would be a solution to the halting problem. Hence, the totality problem is undecidable. So we proceed now to the topic of intractability. Intractability is the solvability of the problem with any algorithm solving it, no matter how clever, runs at least exponential time. Thus, its algorithm has an acceptable running time. For example, is the longest path problem. It runs exponentially. The longest path problem is the problem of finding a simple path of maximum length in a given graph. A path is called simple if it does not have any repeated vertices. The length of a path may either be measured by its number of edges or, in weighted graphs, by the sum of the weights of its edges. In contrast to the shortest path problems, which can be solved in polynomial time in graphs without negative weight cycles, the longest path problem is NP-hard, or non-deterministic polynomial hard, meaning that it cannot be solved in polynomial time for arbitrary graphs unless P is equal to NP. Stronger hardness results are also known, showing that it is difficult to approximate. So proof. Take, take for example the input graph with n number of vertices. Our output must be a simple path of maximum length in a given graph. It does not have any repeated vertices. So if we brute forced it, we will have an exponential running time. To see that the longest path problem does not have optimal substructure, consider the graph in figure 1. The longest path from A to E is AB. The longest path from A to E is A, B, C, D, E. This goes through B, but the longest path from B to E is not B, C, D, E, but rather B, C, A, D, E. This problem does not have optimal substructure, which means that we cannot solve it using dynamic programming. If brute forced, there can be exponentially many such paths. Another example is in the graph shown in figure 2. There are 2 raised to n different paths from vertex 1 to n. So, for the conclusion, the longest path problem is intractable since it has at least exponential running time.